let's go ahead and get started here. Just the goals of this talk are pretty simple. I'm going to focus on data visualization. So I'll have an overview of the material. I want to do a comparison of what we have out there already and show some of the limitations that we can do better. I want to step this up. I want to give you extra tools and information that you can use in your work. There are opportunities that the new techniques present themselves, especially for temporal analysis, and then I'll summarize it at the end. I do want to thank Walter Antonidas for letting me use his data set. And so that was a special case that he was able to do that. And it made it much easier for me to put together the talk for today. So getting right into it, data visualization, traditional graphics. Why do we always have graphics? Well, they're most helpful when they show us the unexpected. And there's a lot more information that's available through tables. Here I have 3 graphs here of from a study showing some surface runoff, some infiltration, and some recharge. But you know what? That only goes so far. We are so full of line graphs that sometimes they kind of blur together. What I want to do is present the raster-based graphic evolution of that. Another term for these types of plots are heat maps, but that only goes so far. There's so much more that we can do with this. There's data subtleties and interrelationships that we're able to see here. Multiple timescales can be seen simultaneously, and new analysis techniques is the fallout from all of this. So Walter was extremely helpful in providing a lot of information here, but because of the time limitation, we're only going to be looking at discharge, head, and then the groundwater recharge. Although if you look at the data sets, all of them are time series. So any time series can be put into this particular format. Looking at the head, the groundwater recharge, and the discharge itself, there's a lot of data here. There's not much information. It's very limited, especially if you have a lot of data to show. It is very difficult to understand what's going on for within and between years for comparisons, because it's lost in this forest of trees, as it were. So what can we do about that? Well, there are some things that are out there that are being used. Here's some graphs from some groundwater data here in Colorado, where I'm located. And this is kind of nice. We do see that we have this ability to create a window of what we're looking at here. And then we can actually shift that window within the period of record that we're interested in. Unfortunately, when you have this kind of a graph, if you have data from an earlier time and a much later time, it's very difficult to do intercomparisons this way. But it's a step in the right direction. Another way of displaying a lot of data are what we call spaghetti line plots. We're taught that these are lines within a single plane. Again, it is difficult to do comparisons within and between years, although it's helpful for looking at extremes. But unfortunately, since we're reusing colors for the different years, even if I see a spike here, I just don't know which year it's associated with. However, it's this plot which opens up the opportunities for us to show the data a little bit better. We're all taught these are lines within a single plane. Well, that's not the case. It looks like that, and I agree it looks like, but that's not what's going on. What we actually have are multiple stacked profiles that we're looking at. There's a dual time scale that's now available that was hidden before, and other views are possible. So we have this mountain range of data, as it were, and the spaghetti plot is looking at this mountain range from the ground. Well, that's very limiting, and that's why it appears as though they're all in the same plane, but they're not. But by seeing the data presented this way, we can see we have a new option to view the data, and that's from the air. Just like you do with a drone or an aircraft for a watershed, you would take it from that point of view, and now we can do that. And how do we do this? Well, here's the steps. They're pretty straightforward. I'm going to combine coordinates and attributes in order to show the data. The x-axis is the day of the year. The y-axis is the year. Now we have a nice rectangular coordinate system. But as far as the data itself, we're going to use the attribute of color for this. I'm going to have a color scale that's associated with the range of values that the raster cells have. And by doing it this way, we avoid a lot of problems on here. Now it becomes a two-dimensional representation of a three-dimensional surface, and we can see each day clearly and equally clear compared to any of the other parts. You may not know anything about this example data set that I have here, but you do see that in year 2012, you see a lot of red. We look at the color scale. That was a very dry year in this case. You can see individual storms, individual days on this. And all of a sudden, the ability to see the interrelationship between the data points is expanded. Now, here I'm using a rainbow colored approach. People often ask me, well, what if someone is colorblind? It's simply easy to readjust and put in a different color ramp in order to address that problem. There's a great free website out there called Color Brewer 2, and it lets you pick a color scheme that would address different types of color blindness that people have. It's a simple process. You recolor your squares. The same concept of using a raster heat map approach is just fine here. So from there, here we go. Here are two graphs, the raster hydrograph and the line hydrograph. These are the exact same data set. And yet, at a glance, you can see there is a lot more information, a lot more detail on the plot on the left side as opposed on the right side. Now, if we look at the line graph, we do see extremes. Now, here's a data point right here that looks like the lowest data point in the information that we have here, but it's pretty tough to find out what the data is and what the events led up to that. It's somewhere between 2006 and 2020, and it's probably closer to the 2006. If we look at this on the raster plot, there it is in the center. We quickly see that it happened in year 2010, and it happened late August, early September. Much easier to find out what's going on the data with doing this kind of a plot here. So that's a big step forward here. Some practices to avoid. People get excited about this. Oh, this is 3D. There's perspective and scale problems. First, you get this kind of a problem. Do not use 3D with the Z value as an axis, because now here we have some what appears to be like bumps in the data surface. You can't see what's going on underneath. Also, I see for the years in the way that the axis is moving, it's tough to see because I wish I had made this a little bit larger, but on the day, the person who was doing this did it every 31 days until they got to the end and they stopped at day 361. So there's anywhere from 5, 6, or 7 days that are not represented on this kind of a graph. Or that first one was from a 1983 publication. This one is from a 2023 publication. And now the perspective is complicating the understanding of what we're seeing here. It's a mess. I know the researchers are trying to do the best they can. This is not a very good way to represent the data. I cannot figure out which each of the points are to project it onto the walls in the back. Here, again, you see the year and the day are not increasing, or they're increasing in a similar fashion, except now this particular person used the default of the program, and you have an increment of every 50 days, which I don't know what that represents. 30 days is about a month. Maybe 3 months is a season, weeks or 7 days, but I don't know how 50 days works into that. Here's another plot. This person now is using the same kind of a thing, but if you look at the year and the day are coming together rather than increasing in different directions there. And they've also have these high points you can't see behind that. What this person tried to do is show the data division in months. But because months are different lengths of days, it causes an inconsistency where the first of the month is. And so by the end, the division isn't the 1st of September, it's the 6th of September. Some other things to avoid here are do not interpolate pixels. In a spatial system, you can move any direction, and it's appropriate to look at interpolation in any direction. If you're talking about time, you can only move forward. The problem is you can't have next year's storm affect your values today. And this is a classic way it's smeared on that. You also see that the graph there at the center, year increases in a downward direction. I call this the calendar approach, because you look at a calendar, the earlier days of the year of the month are at the top, the later days are at the bottom. So you have a tendency to read down. Well, that's not what you would do in a graph. And then finally, the other one you should consider maybe not doing is when you're trying to combine years, months, and days, and you get this kind of a crazy thing. Here, years are increasing down, months go across from left to right, but the days go down, and then they come up over to the next row, column, and then come down that way. So what they're trying to do is divide the days into days of the week. The top is Sunday, and it goes down to Saturday. The problem is that adjacent squares are not adjacent in time. There's a week time between them. And so this becomes very problematic to do this looping effect. Plus, each individual square is outlined. Don't do that. It just confuses and dilutes and diminishes the coloring system that you have there. It kind of makes it more foggy, if I could use a term that comes to mind. So this is a problem. The other problem with this is the division between the months is going to vary from year to year. Sometimes your birthday's on a Monday, sometimes it's on a Tuesday, sometimes it's on Saturday. This is the effect of what you're having here. And so it's difficult to see the division between months for different years because it's all different. What I'm going to suggest is a standardization approach. This is done by the US's Geological Survey, the premier water resource agency in the States. And they had followed work based on my dissertation. I worked with the USGS. They adopted this tool. And what we have is a year on the y-axis that increases in the upward direction. We have the day of the year on the x-axis, and then increases as you move to the left. So everything's in the first quadrant, which makes calculations a whole lot simpler on here. My clock keeps popping off here. I need to keep turning it back on here. Okay, good. So what we have is this standardized grid. If you notice, the division between months is not a set of equally spaced lines. It's actually an overlay of smaller lines. And the smaller lines are coincident with the first day of the month. If you look closely, between February and March, you see that every fourth line is moved over by 1 day. Those are the leap years. This way, we don't have to do anything with the data. There are some programs that ignore February 29th, like it doesn't exist. You introduce a systematic error that way. You don't have to worry about doing anything to the data themselves. You don't want to do anything with the observed data or the calculated data. The calendar is an artificial, arbitrary system that we've superimposed on the year. We don't need to worry about that. Why not make your grid lines variable? In this case, it's just a data overlay. It's just a layer of the letter I on top of when the first day of the year is. That way, everything is exactly the same. You get to the end of the year, you'll have a missing 366 for non-leap year days, and that's it. Otherwise, it looks good on here. Now, what I want to do is show you a program that I use called Surfer from Golden Software. I'm going to hop out of my talk. I'm going to go in and show you some of the things that you can do with Surfer and this way of presenting data. So give me a moment while I stop this. And are there any chat questions that someone can tell me while I make the change? I'm going to stop my share and then start it up here real quickly.
We don't have chat questions for the moment, but if someone does have one, please go ahead. I know often people wait till the very end to put
That's
in
fine
questions.
too. Yeah. Okay, here we go. So can everyone see my screen for Surfer?
Yes, we can see it.
Okay, good.
I can maybe just share the one comment that is in the chat right now that says, "Where were you when I made all the mistakes you described?"
Well, I'm here now.
There we go. So I'll let you continue.
Thank you. That's a nice comment. So what I have here on the right side, my contents, I have all these different layers that I've prepared ahead of time. And you can see that each of these I can turn on and off just like a GIS. So I'm going to focus on flow, head, and recharge as the three that I have here. Before I get going, let me show you something about the color scales. The flow is a logarithmic scale. It also has gradients for here. My head scale, which I'm going to have you make this from green to white to brown. The deeper we go, the lower the value for the height above your reference, your vertical reference, is going to be brown. And that's a linear scale. And then the recharge is, I'm using three different color schemes here. First of all, it's a logarithmic scale here, but there are days when there's zero recharge taking place. Well, if you have zero in a data set and you're looking at a logarithm, it's a problem because you'll have an infinite number of orders of magnitude that way. Here's a trick that you can use to get around that problem. If you look at the bottom of the scale, I found the one value between 0 until the first value. And what I've done is I said, this is 0.1 millimeters or less. So the program will take that value of white and apply it to all other data that are part of the display. This way my 0 comes out looking as white. So even though it's a logarithmic scale, by making that lower value some value or less, you include the 0 values in there and it becomes not a problem here. So let's start with the flow here. If I turn on the flow, this is the one we were just looking at before. And at a glance, you can see that the higher values are more blue. And we see that's pretty much in May when the highest values occur. So nice is those are the raster. I can overlay something like the maximum that takes place. Now, these are the days of maximum flows on the stream flow. And right off the bat, you can see that most of these occur within the spring snowmelt time period around May. But there are 5 other values that are not associated with the snowmelt. What this means is they've come from a different population. It would be inappropriate to use the maximum of all the values, annual values here, to do a flow return period calculation, because now you're mixing 2 different populations on that. This shows it very clearly in what's going on there. So just like a GIS, we can look at point data. If I go back and I turn on my flow, I can also do contours here. And now I'm going to show you, these are a field contour where the flow was 0.1 cubic meters per second or larger. And as I do this, if I turn off the flow itself, well, not a surprise, all of my maximum annual flows fall within that area. So now I've got lines, I've got areas, I've got points. This is exactly like a GIS. In fact, I've used ArcGIS to produce some of these graphs here. I don't enjoy using ArcGIS. It was never made to do that. I use a different program, but there are several different programs in which you can do this. Okay, if I turn off the contours and the flow and the maximum, and I turn on my groundwater recharge, there's that. Now I see there are 4 distinct periods of recharge. There's the winter months, January, February, March. We get May, we get that April, May, spring snowmelt. And then June through September, October, we get this pattern of short duration recharge taking place. Come October, we see that there's this smearing effect. So when the plants are starting to lose their leaves because it's autumn, you don't have the transpiration, that water that might have been lost through root capture and using the transpiration for the plant, that's not taking place. That water then can get into the groundwater system, and you see that smearing effect. So we have a fall period, we have a summer period, we have spring, and we have a winter. So that clearly jumps out at you on this. I can turn that off. I can turn on my wells, and now I have higher wells or levels, right, matching the spring snowmelt. But we see the lowest wells happened, well, gosh, 2010, August, September. If I turn on my flow, yeah, very low water levels were completely consistent with the very low water table levels on that too. A couple things I want to show here, then I'll go back and finish up here. Again, you can do all these things. What I wanted to do, and this surprised me, this was really something interesting that I wanted to do. I have a threshold that I've put together here, and I'll turn these on. I don't need that one yet. I have a threshold here that only a 10 centimeter level is what I'm looking at here. Anything above this threshold I'm interested in, I'm going to make white. Anything below that, I'll make light gray. This was the interesting thing that I found out about this. If I'm looking at December, January time period from about 1990 earlier, I see these big blocks of that particular flow level are occurring, a wintertime level in general here. But over time, I see that more of the days that you have this flow level is occurring more into January, and I see it's occurring less in November and December. It appears as though the whole timing of the system has changed over anywhere from 2 to 4 weeks on here. So by looking at specific flows that you want to examine in this kind of a grid system, you can see some really interesting subtleties on that. And lastly, before I get back into my regular talk, let me go ahead and turn this off. And there's another way of doing lines here. Let me turn off, here we go, the head. And I want to just look at the groundwater level itself. I can go ahead and put onto this a profile, a mid-May profile. And what that turns out to be, where are you? There you are. I've created along this line here, I've created what the water level is on the 1st or on mid-May from year to year. And so I can see how that varies here. I can zoom in here a little bit. And I can, if there's a specific time period that you want to look at, that some sort of activity takes place. Maybe it's before irrigation starts being using the water, or any number of things. This is a way to look at a specific slice of the data for year-to-year comparisons. So that's another nice little feature you have on here. Okay, well, good. I'm going to stop this, get back to what I have to show you. I got a little surprise here, so let me stop the share. Let me get back to my other. There we go. Share this. And I want to make sure I'm sharing the right screen. It looks like I'm not sharing the correct screen.
It's the presenter screen that
Yeah. Yeah. Let me. I have to get in. Oh, here's where I can do it. Here we go. I think this will work. Hopefully that it's paused. Okay, I don't want to pause it. I'm confused. It worked just fine earlier.
It did. We even
Oh,
just
resume share. There we go. Is it still the
it's
the
still the
speakers?
presenter. It's still the presenter.
Okay, let me try something here real quick. I apologize for this. There we go. Is that now correct?
Yes, that looks good.
Okay, good. So I've got my 3 graphs here, and I'm going to use a program called Microsoft Sway. So I need to stop my share and go through this again and find out there it is here. I think this would be good. Can you see the multi-screen here?
Yes.
So now what I'm overlaying is my streamflow and my head. And now I can do a comparison between these 2 levels. And this is only possible because I have the exact same framework. I cannot see how anyone could do this if you have the 3D kind of plots there. And so as I move through here, you can see the difference in how they line up between the 2. This is flow and the head. And I've also set this up so I could do flow and recharge on here. And the last one is head and recharge. So this is a vertical line. You could have it be a horizontal line if you wanted to as well. Stop share, get back to my other talk here. That should be correct. Is that right, Valerie?
Yeah, that works.
Okay. One last thing, then I'll wrap it up here. This was from an example for oceanography. A woman who was studying wanted to know the thresholds of these different characteristics of the sea in order to predict red tide blooms. Red tides, the dinoflagellates, can cause toxins if people eat the shellfish. So it's important to know what characteristics exist. And so she had these 8 different layers here. And she had a workflow. First of all, you do define the criteria, the thresholds that are important for whatever it is you're studying. So each layer has its own particular criterion. You simply apply a binary filter that if a particular day meets that particular criterion, you assign it the number 1. Otherwise, you assign it the number 0. And you do this for all 8 layers. Then you simply add up each of the layers. So each day you'll see how many ones there were for those different layers. And then you'll have the summary layer here. And in this case, this is what we came up with. So we had almost 20,000 points and reduced down to 126 days. And not as just the number of days, we see the temporal distribution of all of this. In this case, we see that in this one year, 1999, there were no days that had at least all 8 characteristics on here. But she was really interested in this one in May, because this is usually a late summer, early fall kind of a phenomenon. Well, if the conditions exist as early as May for public health safety, you're going to have to start taking water samples perhaps in March or April in order to assure that you don't miss a potential bloom, since all the factors that contribute to that can occur rather early in the season. So In summary, the status quo, it is limiting. You can only do so much with that. I'm trying to raise your game, give you more tools to have for what you're doing. The new visualizations that I showed you opens up new options for you. You're going to think of things that I never thought of. The standardization is key for having some of these new analysis techniques, be it the slider, the threshold, all of that, very GIS-like, is incredibly important. And we have basically a new kind of a GIS. And the guy who started ESRI, Jack Dangerman, had this great quote I wanted to use today was, the application of GIS is limited only by the imagination of those who use it. Here's an example where now, if you have GIS skills, you can apply them in this absolutely brand new direction on that. And with that, I say thank you. And I say if there's any questions.